welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. The interaural level differences that we use to localize sound sources are much more nuanced than simply those due to diffraction. In this video, we'll learn about all of the details of binaural frequency filtering that we use to localize sounds.
So let's get started. We now know that at low frequencies, there's minimal diffraction around the head, so there are minimal level differences between the ears. And as a result, humans use interaural time differences to localize sound sources. Yet at higher frequencies, the time of arrival between ears is relatively useless to use for source localization due to spatial aliasing phenomena. So the diffraction is high in this instance, so humans use that interaural level difference to localize higher frequency sounds. But if we only used ITD and ILD to localize sounds, we would find that we cannot easily differentiate source locations for elevation angles that are out of the azimuthal plane. And this is called the cone of confusion. When the ITD and ILD are relatively the same for this model of the head as a rigid sphere, we are unable to localize sounds out of the azimuthal plane. There must be other mechanisms that we use to localize sound sources. In fact, there's very nuanced frequency filtering that we would find different from a rigid sphere to the human head. If we take a test of a speaker moving around a sphere where there's a microphone around the right side of the sphere, we would plot out a map like this, where we have the ratio in the frequency domain of the microphone with respect to the speaker amplitudes. So the microphone in the spherical head shows an increase in the received acoustic pressure around 90 degrees, which is of course when the speaker is directly transmitting at the microphone. But when the speaker moves to 270 degrees in the azimuthal plane on the opposite side of the microphone, there's a very low level of sound that's radiated to that side of the head. We see the frequency dependence of this as well. Also note that there's very little influence at low frequencies on this diffraction phenomenon. Now, compared to the rigid sphere, the human head has very many nuances of geometry, and these all affect diffraction, and they assist our localization of sound. The corresponding measurements on a human head show many nuances that do not show up for a perfectly rigid sphere. For instance, when the speaker moves around to 90 degrees, at some frequencies there is not as much gain as at others. But when the speaker moves around to 270 degrees, there's significant blocking of sound. Multiple factors affect these unique filtering characteristics. First and foremost are the pinna. The pinna, or the auricles, on our head, they provide significant filtering as sound propagates down the ear canal. Pinna collects sound over a larger area than the ear canal itself. We see this especially with animals that have very large ears that help to pick up sound at long distances. As we look at the human pinna, the concha, the crus, the tragus, and the other cartilage that make up our pinna are unique for each person. So every person has unique frequency filtering for what they hear. Listen to sounds outside and move around your pinna and experience how substantial the filtering changes for what you hear. This is great evidence that the pinna are critical for the frequency filtering that we hear to localize sounds by ILD. But many other aspects of the body also assist to filter frequencies that we hear. Our torsos and our bodies reflect and diffract sounds up to our ears, and these help to enhance our filtering and localization mechanisms. The motion of our head and ears can also significantly improve our ability to localize sounds. Animals are very good at this. You'll see many instances with felines doing this around the house. The head-related transfer function is the frequency domain relationship that we would measure from source to what the ear hears, the HRTF. This is one example of an HRTF for a human head. We see this type of amplitude relationship plotted here. There's also a corresponding phase relationship that's not shown in this plot. HRTFs vary from person to person, and general HRTFs can be measured by mannequins that have soft ears and microphones in their ear canals. HRTFs are used in a wide variety of sound virtualization algorithms. To summarize what we've learned, in addition to ITD and ILD, our means to localize sound sources is aided by numerous frequency filtering behaviors of the components of our body, and these help to eliminate this hypothetical cone of confusion. The head shape, the pinna shape, and the torso all contribute to provide distinctive received sounds in the eardrums between the left and right ears. The head-related transfer functions, the HRTFs, characterize the differences in amplitude and phase from a transmitted signal to what is actually received at the ear.
That's it for this video. In the next video, we'll learn how these nuances of binaural hearing can be reproduced with binaural audio.